5.2 is about binomial probability distributions. So the word binomial usually refers to two. Bicycle, two. So binomial probability distribution results from a procedure that meets the following requirements. So this is still a probability distribution, or you're looking at x and p of x. But in this case, we only have two options rather than the options like we had before where you can get x is 1, x is 2, x is 3. So we are going to look at the binomial. The procedure has a fixed number of trials. So we'll look at what n is. N is your number of trials. Trials must be independent. So whenever we talk about independent, we're talking about the outcome of any trial doesn't affect the probabilities in the other trials. So if you see the word with replacement, then that means it's independent. Or spinning a spinner is independent. Each trial must have all outcomes classified into two categories, success or failure. Success and failure doesn't mean good or bad. Success is just what you want. So let's say I want to find the probability of having a boy. Then I would say my success would be boy. So my failure would be girl. So an example would be success, boy, failure would be girl. Another example would be, let's say, answering the question with yes would be success. So no would be failure. Or if we say we're flipping a coin and let's say tails is success, so then heads would be failure. So there's only two options for this. One last one would be, let's say the answer is correct versus an incorrect answer. So just think of success as what you want. Probability of success remains the same in all trials. So like tails is always 0.5. Let's say you have a multiple choice test. Each answer has 4 choices. So correct would be 0.25. Incorrect would be 0.75. Here's some new notation for us. So S stands for success. You're going to name what is considered success. Failure is the opposite of success. PS, or just a lowercase p, means the probability of success. And PF or Q is going to be your probability of failure. N is what we talked about a minute ago, your number of trials. X is how many successes you want out of all the trials. Number of successes in the trials. P is your probability of success. So I'm just going to put PS. We're going to use some formulas that involve N, X, P, and Q. So you just need to know that P is your success, probability of success, and Q is your probability of failure. we're going to use these to find P of X, which is your probability of getting exactly X successes in trials. So we're kind of going backwards a little bit. If we look back at our first page of 5.1, we were given this. Well, what we learned today is going to show us how you could find each one of these numbers. So on this, the N was 12. X was how many successes, which a success would be how many Mexican Americans were chosen. And then our probability of success is 0.8 for every single trial. So we are going to learn how to fill in a chart using the given information. So be sure that X and P both refer to the same category being called success, where a success doesn't necessarily represent that something is good, but rather that a certain outcome occurs. So you're looking at what you want. Use the 5% guideline for cumbersome calculations. When sampling without replacement, so without replacement is considered dependent, unless you have a really big sample population and you're only taking a small sample size. So if you multiply 5% times how many are in the total population, then you can find out if you can just use independent or consider the event to be independent, rather. Okay, we need to determine whether a given situation is considered binomial distribution. So let's look at our example that we had from the very beginning of chapter 5, which it says, if we need to select 12 jurors from a population that is 80% Mexican American, and we want to find the probability that among the 12 randomly selected jurors, exactly 7 are Mexican American. So we would look at these 4 things. Is the number of trials fixed? What would be the number of trials? 12. Yep, that's your N. Go ahead and label it in your paragraph or your problem example. So I'm going to put N equals 12. So is the number of trials fixed? Be a yes. Are they independent? Well, if you take a juror out, are you putting the juror back in? They're dependent, but remember that cumbersome calculations, we're going to consider it to be independent. Our sample size is only 12. Think of 5% of the population. Is 12 less than 5% of the population? Most likely. So we are going to say yes. We're going to consider it to be independent due to how large the population is. Does each trial have 2 categories? Yeah, what are your 2 categories? So yes, success would be Mexican American. So failure would be the opposite of that. So that would be non-Mexican American. Does the probability of success remain the same in all trials? What is the probability of success? How many? It says the population is 80%. So your probability of success is 0.08. Or 0.80, sorry. So if all of these categories are a yes, which this was a yes, then yes, it's a binomial distribution. Yes, meets all requirements. So from this, we are going to identify the values N, X, P, and Q. So N is your trials. So we already said that there are 12 fixed trials. X is how many we want. So we want to find the probability that among 12 randomly selected jurors, exactly 7 are Mexican American. So 7 is what you're looking for. It's X. 7 is X. P is your probability of success. Out of the whole population, how many are Mexican American? 80%. Yep. So 0.0 or 0.80. So Q is non-Mexican American. It would be what? Yep. Because we know P plus Q is going to have to equal 1. It's our whole distribution, all of it, 100%. Okay, let's go to the next example. If we want to select 2 girls from a family of 5 children, let's look and see, is this a probability binomial distribution? Are the trials fixed? How many trials are there? Yeah, 5. Yes. I'm going to go ahead and just put it down here since we already know that's there. Are the trials independent? So if I have a girl, my next one, does it depend on what I've already had? Or is it completely new? Really has no, it's independent. Because one doesn't depend on the other. Because somebody could have 5 girls in a row. It's just what happened. It's not, one doesn't depend on the other. So are the trials independent? Yes, they're independent. Independent of one another. Are there 2 categories of outcomes? Your only outcomes would be boy or girl, right? But what's considered success on this? Girl. And so failure would be boy. Does the probability of success remain the same? Yeah, what's the probability of having a girl in a birth? What are your 2 options? Yeah, so it'd just be half. It'd be 0.5. Probability of success is 0.5. So since all these requirements are met, yes, it's a binomial distribution. So X is what we want. We're wanting to find what is the probability that we select 2 girls. So that's X. It's what you want. Probability of success is P, so that's 0.5. Probability of failure, probability of getting a boy is 0.5. Okay, I'm going to fill in down here too. What we are going to do with these values is we can actually find mean, variance, and standard deviation. So let's write the formulas for that. For binomial distribution, we can find the mean, which is mu. It's found by doing n times p. The average number, the mean number of births on this one would be 5 times 0.5. So it'd be 2.5. Your variance will be the next thing you can find using the n, x, p, and q. This is found, so it's sigma squared. It's found by doing n times p times q. And then your standard deviation, I'm going to abbreviate it, is just sigma. And you can find that by taking the square root of n times p times q. Square root of your variance. We are also going to use the range rule of thumb to find your unusually high and usually low values. Your range rule of thumb is, we've set up this number line a couple of times where you have mu in the middle. Unusually low values are where you take mu and subtract 2 times your standard deviation. These are unusually low or significantly low. And then mu plus 2 sigma. So you're doing 2 standard deviations above the mean. That's considered unusually high. So I want to do an example of this. So I passed out a half sheet of paper. There's one on the notes drive also. So if you need to print that out or just kind of put the information here. I'm going to go ahead and show y'all that. So this is an example from Pearson where we find mean, standard deviation, and then the range rule of thumb to find unusually high and unusually low. Assume that hybridization experiments are conducted with p's having the property that for offspring there is 0.75 probability that a pea has green pods. Assume that the offspring peas are randomly selected in groups of 32. Complete parts A through C below. Find the mean and standard deviation for the number of peas with green pods in groups of 32. So let's find N and we'll use P and Q. Sorry, y'all can't see that. We're going to use these variables to find the mean, standard, and standard deviation. So N is how many trials are there. So how many trials did it tell us that we're going to be given? How many? Yeah, 32. What's the probability of success? Well, what is success anyway? Yeah, green. Green pods. So our probability of success, they gave us here, 0.75. So then what's the probability of failure? 0.25, yeah. So you take 1, subtract 0.75, and you get 0.25. So once you identify those variables, then you can plug it into the formula. So let's find the mean. It's N times P. So the value of the mean is, we're going to round, type an integer or decimal, do not round, because this is discrete. So N is 32. We're going to multiply times the probability, 0.75. It's 24. So the mean is 24. So 24 out of the 32 will have green pods. The value of standard deviation. So we first have to find variance. Is N times P times Q. That's your variance. And then standard deviation, sigma, is found by doing square root of that. which we could just put it in just like that. Take the square root of n times p times q. So I'm going to put in square root of 32 times 0.75 times 0.25. This one says to round to 1 decimal place as needed. 2.4. Use the range rule of thumb to find the values separating results that are significantly low and significantly high. So let's look at significantly low. To find significantly low, you're going to take your mean and subtract 2 standard deviations. What you can do is you can use what we found, 24 minus 2. I'm going to go up and grab this so that I'm not rounding anything, just to be sure. So I scrolled up and then pushed enter to bring this down into my parentheses, close parentheses. So the values of 9.1, oh, I put it in the wrong spot. 9.1 are significantly high. Let me erase this one. So then significantly low or high, keep on getting these confused, sorry. I can go up here. I'm going to change this to a plus. So round to the 1 decimal place, so 28.9. So anything between those is usual. So if you want to look at it, here's mu, which is 24. So unusually high number of p's would be 28.9. So anything above this is significantly high or unusually high. And then 19.1, anything below that is significantly low. So anything between those is considered usual values. So part C says the result of 15 P's with green prods is a result of 15 P's with green prods a result that is significantly low, why or why not? Where would 15 fall in this number line? It'd be over here. So let's fill in the blank. The result is significantly low because 15 P's with green pods is less than 19.1 P's. Okay, let's keep on going. We have 3 methods for finding the probabilities corresponding to the random variable x in a binomial distribution. Remember, all probabilities should be rounded to 3 significant figures. So what we're finding is, we're going back to this. We're learning how to find these numbers here when we can't list everything. So one of the ways is using this formula. To use the formula, you need to know N, X, P, and Q, which we know in each one of these. So we'll do this example to find P of 7. So find the probability of getting exactly 7 Mexican Americans when 12 jurors are randomly selected from a population that is 80% Mexican American. So N is your number of trials. So that is your 12 jurors that you're selecting. X is what we're finding the probability of. So exactly 7. P is your probability of success. So success would be getting a Mexican American, so that'd be 0.8. And Q would be probability of failure, 0.2. So in order to find P of 7, we'd use the formula. So we have the formula up here. So let's plug in n factorial, so n is 12 factorial. And then parentheses n minus x, so n minus x, 12 minus 7 factorial, x factorial times p raised to the x value, x is 7, times q raised to the n minus x. So the other trials would be 5. There'd be 5 left. So these two exponents should add to be your total number of trials. And we can plug this into the calculator. Almost forgot where factorial was. That's under math probability. Okay, once you put it in the formula, it comes out to 0.0531. So, not 1, because it said 3 significant figures, 0.053. So if we look back at our notes from the beginning, look, there it is, 0.053. So this is just a way of checking our work. All right, let me teach you. There's also using a appendix. So I put the appendix at the back of your paper. So we are going to do this example, but with the appendix. So it says locate n and the corresponding value. This one doesn't have an n of 12. So the problem with the appendix is sometimes there's not enough data on here. So like we would look at n being 12, but this one only goes to 8. So we can't use the appendix on this one. So we are going to do this one thing. So the probability of exactly 2 girls out of a family of 5 children. So we need to write down what our n is. N is how many trials? 5. X is how many do we want successes? We want exactly 2. And then the probability of success is 0.5. So let me show you how to use the appendix, the table. So we go to n being 5. So you've got to look at what you're given. So n, you're going to go down to 5. 5 trials. And we want to know what the probability of having exactly 2. So I go to 2. And then I look at P, probability of success. What probability of success is there? 0.5. So we look here, and then we match them up. 0.313. So you first start with your n, then you go to what you want, which is your x, then the probability of success, 0.313. So the probability of getting x being exactly 2 girls, 0.313. Okay, the next one is kind of tricky with its wording. It says probability of having at least 2 girls out of the family of 5 children. So what this means is you still have n equals 5, but your x is going to be at least 2 children that are girls. So x is going to be greater than or equal to 2. And our p is still the same, 0.5. But you're going to have to find the sum of all of the options. So the options would be probability that it's 2, probability that it's 3, probability that it's 4, and probability that it's all 5. And you would add them all up. So we already have the probability that it's 2. We already found that one. So we're going to use the table again to find the probability of 3. So the only thing that's changing is the x value that we're looking at. This one's also 0.313. Then probability that it's 4, 0.156. Probability that they're all 5 girls. It's a lot lower, 0.031. So we add up all of those probabilities together to get the probability that x is greater than or equal to 2. So you added them all up. Awesome. $813. Is that what y'all got?
Yes.
Yeah. So that's a pretty high probability that you're going to have at least 2 girls. Okay, we're not going to do that. There is a way to use the calculator, though. That's the third way. Yay, calculator, right? So look at number 3. Using the calculator, you go to stats. We're not going to do that. We're going to do binomial PDF distribution. So it's actually, we're going to do second vars, which is called distribution. So see how it has distribution there? Second. So we're talking about a distribution. Now look at all the possible distributions. I'm going to go down. We're going to do binomial PDF. It's A. So we're talking about a binomial probability distribution function. That's how you know this is the function you're going to use. Binomial probability distribution function tells you what kind of function we're dealing with. So select it. Let's do this one to find the exact. So this is the example one. There were a total of 12 trials. Probability of success was 0.8. The x value that we were looking at was 7. We push enter, and it's 0.0531. It's the same thing that's here. So this is the one that we can use to find each. If we want to find multiple, though, you're going to have to do each one individually and then add them together. So go second vars. We're going to go back to binomial PDF. And on this one, we had 5 children. Probability of success was 0.5. The x values were 2, 3, 4, and 5. So we're going to put in 2. And then it gives us that amount. And then if you're using the same information, you can actually arrow up and bring it down. And the only thing you're changing is the last number. So that would be 3. And then go here. We want 4. See how we're getting the same numbers? We're actually getting them a little further out, so more exact. And then we have one more. We need to find the 5th one. And then you would go and highlight them and add them. So I'd say this plus that plus that plus that. 0.8125. So we can use the formula, we can use the table, and we can use the calculator. I'm going to show you 2 more examples tomorrow. Okay, I think we're out of time now.